Hello everybody, here we are, we have a demonstration about AI-enabled physical ear security using radiofrequency fingerprinting. So I will run you through a demo. We make it gamified so it's a bit more engaging, and hopefully at the end of this demonstration you will know more about radiofrequency fingerprinting and how we can make physical ear security better. Okay, so we have a first use case here in which we have trained our algorithm on some devices, three devices that we have here. So here in this first demo, we just authenticate them. So all devices are part of the machine learning. In the gamification, we are an RF engineer that will try those radio frequency algorithms to make security in the company better. So radiofrequency fingerprinting is the fact to authenticate radios based on unique signatures due to defects in the radio hardware. Those defects are always there, and there's no way to remove them. And then they are also part of the transmitted signal. So our machine learning algorithm will recognize the different devices based on the radio signatures due to those very subtle manufacturing defects. For this purpose, we have an authentication signal that is a 5G NR signal, 2.5 gigahertz, and we push the radio at the maximum of a gain just to have more non-linearities, for example, coming from the power amplifier. It's a very short transmission, 1.4 milliseconds, and just one push slot for 5G. So now we go through it. I will choose the most difficult use case because we have two devices that are exactly the same. And then can the machine learning algorithm differentiate them? That's what we will see. So I'm now selecting one of those small devices, let's say this device 3, and I'm launching the authentication. And then Anastasia will run through the machine learning things.
Right, so after transmission has been completed, we're using pre-trained neural network, convolutional neural network, and we run the inference on the signal. And we are able to successfully authenticate the devices. So this slide shows how actually our classifier is well trained. So you could look at the confusion matrix and see that we have almost 100% accuracy for 3-device classification, even having device 2 and 3 being of the same manufacturing, the same type of which you can also see how well the extracted features by machine learning are well separated in the feature space, which makes our model, but also leveraging unique signals, unique and being very good results.
Now, what we will do very quickly, we will put ourselves in the skin of a hacker. So we will try to launch what we call an impersonation attack. So we have a device here, and we will launch an impersonation attack, meaning that we will use another device that is exactly the same to send a signal that is exactly the same than this one used for authentication, with the exact same settings, and we will see, can we defeat the machine learning algorithms? This is what we will see now. So I'm just going quickly through it. I'm selecting the radio that is the closer, and we use the exact same signal than what has been used for authentication. And now we will see if it works. This is very challenging. This is something we call open set scenario in the community. And obviously, the attacker radio is not seen in the training. So the machine learning algorithm never saw this radio coming. And we will see if it can classify it as an unknown device, or we try to tie it to another device that has been seen in the training.
So actually, attack was not successful. So our algorithms was really well trained and be able to separate a known class from a very similar one used in the training from the same device type. So we're using the convolutional neural network. In addition, we use anomaly detection to actually detect a known class as anomaly. And being very challenging, we still managed to get the results successfully.
Thank you for your attention.